So today we will talk about the atomic model of a gas. We'll talk about molecular speed and temperature. We'll talk about some pressure, and we'll talk about the ideal gas law today. And I will separate this in portions so that it will be a little easier to understand. So let's clear it and get started. Okay. Who recalls what I mentioned about temperature? Very good. Temperature, recall, is the measure of the average kinetic energy of all the molecules that are in a particular substance. So recall this point. So recall the definition of temperature, which we'll write it down here, is the measure of the average kinetic energy of the atoms. Of a particular body, or substance, or whatever you want to call it. Recall this. This is from earlier this is from last chapter. Now, something very important to be able to tell you about it, because we talked a little bit about it last time, not too much detail. The mole tells us the number of molecules and the number of atoms and something. So when I'm looking at something from a certain perspective, each molecule, every one of them, let's assume it's something like that, these are completely random, something like this. This has a velocity, this has a velocity, this has a velocity like that, this has something velocity like that, and they're all traveling at different speeds. Okay, here this is random, and quote unquote random, we should say, and with these different velocities, it would be extremely difficult to measure every single velocity of every single atom that is in here. It would be very difficult to do. So with our temperature, we measure the average kinetic energy of this. And we can recall this equation that you can recall how we measured this earlier, that the average kinetic energy is 3/2 this Boltzmann's constant multiplied by the temperature. Okay. And you can certainly remember this. And so, this is kind of the connection between temperature and the kinetic energy averagely, like that. And certainly we recall that the kinetic energy of any substance, at least when working with this, mass times velocity squared or mass times speed squared, like that. Okay? This is certainly true. Certainly this is the case. Now, because we have a bunch of different molecules, how do we get the average kinetic energy of all these molecules? Right? Well, we take kinetic energy and of course we divide by the number of molecules that we have. So in this case we'll dub this capital N. Okay? And so we have average kinetic energy is 1/2 mv squared divided by number of molecules. Okay? And divide by the number of these molecules that you have, because each individual molecule will have kinetic energy. And so to average them out, we divide by the number we have, whatever that is. Doesn't matter what it is. Okay? And so now we want to try to connect the speed of the molecule. We want to figure out the speed of these molecules, like this. Okay. And so we can call this speed here, this velocity, average speed. So we call it like this. And then we have this expression here. We have this expression, kinetic average, kinetic energy, is that you have this Boltzmann constant multiplied by the temperature. And so we can connect the two of these together. Okay. So to connect them together, we can do like this. We'll equate the two quantities. So we have 3 halves. Okay, so B times temperature is 1/2, and V average squared like this. And of course, as you can see here, we're solving for the average speed here. So if I multiply both sides by 2 and divide by m, 2's cancel, m cancels, so we end up with V average squared equals 3 kBT temperature over to the mass. And then if I square root both sides, I get the average speed is going to do square root of 3 Boltzmann's constant times temperature over the mass, like that. Okay? And of course, we do things in SI units here. So, as you remember, um, temperature must be in Kelvin. It cannot be in degrees Celsius or Fahrenheit or any other system. It must be in Kelvin. And mass will be in kilograms. And Boltzmann constant is one which you'll have memorized now, is 1.38 times 10 to the negative 23rd joules per Kelvin. Okay? Yeah. Okay? Everybody understand kind of what we're doing here. We want to be able to connect the speed of the molecule to the temperature that is given. And so we've done that here, and that's what this formula represents here. All right. Everybody with me so far? Let's clear this up. Okay, now, let's do example. Okay. So your book has an example of the speed of the air molecule. Okay. We'll do something similar to this one here. Now change the numbers around. Okay. So let's do an example with this type of problem. Okay. So our example. So we're considering some oxygen molecules. Let's say we have oxygen molecules. At a temperature negative 129 degrees Celsius. Okay. And then, let's say, and I want to find the average speed of the molecules. I want to find of the oxygen molecules. And then after I want to find the average speed of the oxygen molecules, nextly I want to figure out if mm, let's see, um, at what temperature would the speed be twice what is computed. Okay, this is our nice little example. So, for the solution, we are given the temperature is negative 129 degrees Celsius, which will convert right away in well, it is going to be how we say it. First, we'll convert our number straight into Kelvin. Okay. So I want you to do that right away for me. 129 plus 273, 144, 144 Kelvin. And of course, the mass of oxygen, we can figure it out from using periodic table. Okay. Although it wasn't given to us again, we're under anything that's not anything that you have to define. In this case, the mass of the oxygen can be assumed to be given because it will be on a periodic table. Okay. And so mass of the oxygen is, of course, going to be 32 of the atomic units here. Right, because oxygen is diatomic, and we'll convert it right away to kilograms, 1.66 times 10 to the negative 27 over 1 unit. And so we'll convert it right away. There it is. Okay. That times 32. And we have mass of this in kilograms is 5.4 times 10 to the negative 26 kilograms, like this. Okay. All conversions we do in the given step, so this way we don't have to do it when we do the actual calculations. Then we want to find, of course, the V average. This is sometimes called root mean square speed, or VRMS, but we'll call it the average because it's what I'm used to. So in this situation, for the first part, we simply do so we get it. So we say V average is equal to square root of 3 Boltzmann constant times the temperature over its mass, like this. Okay. And so using that equation, I want you to plug in the numbers here, and you'll get a certain solution for that. Okay. Boltzmann's constant, 1.38 and 10 to negative 23. So 3 times 1.38 e to negative 23 times 144 Kelvin, which is that, divide by 5.04 negative 26 equals this number, square root of the answer, and we get 343. And this, the average is going to equal square root of 3 times 1.3 times 10 to negative 23 times 144 over 5.4 times 10 to 26. That will equal 343 meters per second, or 344, if I round it correctly. 344 meters per second. Okay, that is roughly the speed of sound in air. And it's a reasonable answer. And so then it says at what temperature for part A? This is the answer for part A to the problem. And I'm going to go ahead and erase it. I'm going to go ahead and erase it like this. Here. Okay, implement for part B of our problem. Here it says, at what temperature will the speed be twice what is computed? So we just found the speed at 343 meters per second. So we can say twice V equals 3 okay, so V times T over mass, square root, square both sides, and we'll solve for temperature. We'll solve for the temperature here, symbolically. It's 4V squared the V we just found, so it's equal to 3 okay, dt over m. And of course, if I divide by 3, so if I multiply by the reciprocal of m over 3kb, I get temperature is equal to 4 v squared m over 3kb at this point. Okay. So, and using the numbers we just have here already, so it's 4 times 344 squared, multiplied by the mass, which is 5.4, and 10 to the negative 26 power. Then to divide that by 3 times, make sure you use parentheses in your calculations, so this way it doesn't screw up your calculations, negative 23. And we get T, the temperature, exactly, temperature is 617 Kelvin. Alright, 617 Kelvin, after doing your math correctly. Now, if we change this into degrees Celsius, subtract 270, we get the temperature is 344 degrees Celsius. This is extremely hot. So this doesn't happen on an Earth's surface at all. So I don't think your other forecaster will say something like, oh, it's going to be 344 degrees Celsius today. If you say that, you might want to worry, you might want to check whether you're in hell or not, something like that, because that is extremely hot. So you will not see this temperature in your everyday experience. You can make it in a laboratory perhaps, but not in a situation where you'll be on the surface of the Earth like that. So we'll take a break and we'll come back and we'll talk about pressure next. So this is kind of a simple example, a little different from the one from the book.